Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever get a sense that you might be seeing things that aren't really there, especially when you are looking at a lot of data? Well, a group of researchers has been looking into just that when scientists use a popular statistical tool in psychology and how it can sometimes lead them astray. Let's dive into this. Imagine you are a scientist testing lots of different ideas. You want to know if something you are studying has a real effect, like if a new learning technique actually helps students, or if a certain drug makes people feel better. You use statistics to help you decide. One tool that has become really popular is called the probability of direction, or PDD for short. Think of it as a way to measure how confident you are that an effect is going in a specific direction, positive or negative. If the PD is really high, like over 0.975, scientists might say, aha, we have evidence for this effect. It is like a signal that the data is leaning strongly one way. But here is the tricky part when you test a lot of different things and you use this high PD means real effect rule over and over. You start to run into a problem. It is a bit like playing a slot machine. If you pull the lever 100 times, you are almost guaranteed to get some wins just by chance. This paper argues that when researchers look at many different effects, and they only highlight the ones with a high PD, they can end up with a lot of misleading conclusions. They're missing a key piece of the puzzle, the idea that many of the things we test might actually be nothing. The researchers realized that people using this PD tool weren't really accounting for the possibility that for each thing they test, it might just be a fluke. They call this the prior probability that the data-favored direction does not reflect a genuine effect. In simple terms, it is the chance that the effect you are seeing is just random noise. A coincidence. When you test many things, this chance of random noise showing up as a real effect goes way up. So what did they do? They came up with a clever way to adjust this probability of direction. They call it a prior odds adjustment. It is like adding a dose of healthy skepticism. It asks researchers to think about how many of the effects they're testing they expect to be null, meaning they don't actually exist, by being upfront about this expectation. They can make the PD value more honest. This adjustment doesn't change how they calculate the initial effect, but it adds a layer of common sense for multiple tests. It is like saying, okay, I found a strong signal, but given how many things I am looking at, maybe I should be a little more cautious before I declare victory. Let's get a little more specific about the probability of direction. Imagine you are testing if a new teaching method increases test scores. Your data might suggest the scores went up. The PD tells you the probability that the true effect, whatever it is actually positive. If it is 0.986, it means there is a 98.6% chance. The effect is positive now if you also look at the credible interval, which is a range where the true effect likely lies. A high PD often means that 0 is excluded from that range. This sounds good, right? It sounds like pretty strong evidence. But here is where the multiplicity comes in. When you do one test saying PD is high, so there is an effect, that is one thing. But what if you do 10, 20, or even 100 tests? The chance of just getting a high PD purely by accident increases dramatically. Think about it. If you roll a dice 10 times, you are pretty likely to get a 6 at least once. If you then declare, wow, rolling a 6 is significant for me, it is not that meaningful because you roll the dice so many times. The researchers actually ran simulations to see how this works. They looked at situations where there was no real effect, the null hypothesis was true, and saw how often the PD still managed to be very high. They found that with bigger sample sizes and not using a very skeptical prior belief, the chance of getting a falsely high PD was pretty consistent. They also explored using skeptical priors. This means starting with a belief that effects are less likely to exist. This can help reduce those accidental high PDs for individual tests. But, as they point out, it doesn't solve the core problem of doing many tests. The chance of at least one of those tests showing a high PD due to luck still goes up. To understand their adjustment, it helps to think about odds. Instead of just looking at the probability of an effect being positive, they look at the odds of it being positive versus being negative or 0. This is a slightly different way of framing the evidence. This is where the magic happens. Their adjustment takes that original PD and modifies it based on how many tests you are doing and how skeptical you are that there are any real effects to begin with. They introduce a value called pi0, which is the prior probability that a test is truly null. If you think half of your tests are likely to be null, pi0 would be 0.5. The formula then adjusts your PD. This formula essentially says that your adjusted probability of direction will be lower than your original one, especially if pi 0 is high, meaning you expect a lot of your tests to be null. The more skeptical you are, higher pi 0, the stronger the evidence needs to be for you to consider an effect real. This figure shows how this adjustment works. On the left, you see how assuming a certain probability that all your tests are null makes your prior belief about each individual test's null status more skeptical as you do more tests. On the right, you see the effect on the PD. Weak evidence gets penalized much more heavily than strong evidence. If you had a PD of 0.6, meaning not that strong to begin with, and you are very skeptical that there are real effects, your adjusted PD can drop significantly, maybe even down to the minimum of 0.5, suggesting little to no directional evidence. When scientists do multiple tests, they worry about two main error rates. One is the false positive rate, FPR. The chance of wrongly claiming an effect exists when it doesn't. The other is the false discovery rate, FDR, which is the expected proportion of claims that are actually false discoveries among all the claims made. The paper explains that their adjustment helps control this FDR. By requiring stronger evidence when you are more skeptical or doing more tests, you naturally reduce the number of false discoveries. To test their idea, the researchers ran a big simulation. They created data where they knew how many true effects there were versus how many were just noise. They then applied their adjusted PD method and compared it to the regular PD method. This figure shows the results. Panel A is the false discovery rate. When they used their adjusted method, where pi 0 is not 0.5, meaning they are being skeptical, the FDR was much lower, especially when there were a lot of true nulls in many tests. The unadjusted method, where pi 0 is implicitly 0.5 and no adjustment is made, shows a much higher FDR, meaning more false discoveries. Panel B shows power, which is the ability to find real effects. As expected, being more skeptical. Higher pi 0 tends to reduce power, meaning you might miss some real effects. This is the classic trade-off, control more errors, but at the cost of potentially missing some true signals. This figure looks at the family-wise error rate, which is the probability of making at least one false claim. Again, their adjusted method is better at keeping this error rate low, especially when they are skeptical about the presence of real effects. They also compare their method to other Bayesian approaches for handling multiple tests. They found their method offers a good balance between controlling for errors and maintaining statistical power. To make this practical, they developed an R package called Multibase. This package allows researchers to easily apply their adjustment method. They even provide a worked example using real psychological data. In the example, they took data from a study on ego depletion and reaction times. After running a statistical model, they got several different effects to test. They decided to use a pi 0 of 0.7, meaning they were quite skeptical and believed about 70% of the effects they were testing were likely to be null. The output shows how the original probabilities of direction were adjusted. For very strong effects, the adjustment didn't change much. But for weaker effects, the adjusted PD dropped significantly, sometimes even down to the minimum 0.5, indicating that with that level of skepticism and multiple tests, the evidence for those weaker effects wasn't as convincing anymore. So what is the big takeaway here? The researchers are saying that the probability of direction, while useful, can be misleading when used across many tests without considering the possibility of chance. They are advocating for a more honest approach by making our expectations about the prevalence of real effects explicit. This prior odds adjustment is a way to incorporate that healthy skepticism. It is not about changing the science of how we estimate effects, but about being more rigorous in how we interpret those effects when we're looking at many of them at once. They stress that researchers should justify their choice of skepticism level, or pi 0. A higher level of skepticism is good for exploratory research where you are casting a wide net, while a lower level might be fine if you are testing a very specific, well-established hypothesis. They also acknowledge that their method has limitations. One is that it assumes all hypotheses are exchangeable, meaning they're treated similarly. In reality, some hypotheses might be more plausible than others from the start. Also, this method doesn't give you evidence for a precise null effect, like an effect being exactly 0. Instead, it focuses on directional claims. Not finding evidence for a directional effect doesn't automatically mean there is evidence for a 0 effect. Ultimately, this paper is a call for more thoughtful statistical practice, especially as Bayesian methods become more popular. It highlights that simply applying a rule like high PD means an effect, without considering the context of multiple testing, can lead you down the wrong path. Their adjustment provides a tool to make those decisions more robust and less likely to be fooled by chance. It is about being more careful and more aware of the statistical landscape you are exploring. And that is this week's dose of science from Rubin's Mind Lab. What do you think about this new way to adjust statistical findings? Have you ever suspected you or others might be seeing signals in the noise? Let us know in the comments below. If you found this helpful, please hit that like button. Subscribe for more brainy content and ring that notification bell so you don't miss our next exploration. Until then, stay curious.